Hello and welcome. Ever feel like our computers, despite getting faster, still struggle with complex tasks like true artificial intelligence or consume way too much power? For decades, we've relied on a design called the von Neumann architecture. Think of it like having a chef, the processor, constantly running back and forth to a separate pantry, the memory, for ingredients. This back and forth creates a traffic jam, a bottleneck, wasting time and energy. But what if we design computers more like the human brain? That's the fascinating idea behind neuro-inspired computing. Instead of separating processing and memory, it takes cues from our own neural networks. Our brains are incredibly efficient, processing vast amounts of information simultaneously using interconnected neurons and synapses. Neuro-inspired systems try to mimic this. A key idea is in-memory computing, where calculations happen right where the data is stored, eliminating that energy-hungry commute between processor and memory. Imagine the chef having all ingredients right at their station. Technologies like memristors and phase-change memory act like artificial synapses, storing information and helping compute at the same time. Furthermore, just like the brain processes things in parallel, neuromorphic systems use massive parallelism. They also often copy the brain's trick of using spikes, only sending signals when necessary. This event-driven approach, especially in spiking neural networks or SNNs, makes them incredibly power-efficient, only using significant energy when actively working. Some even use analog computing, processing continuous signals rather than just digital ones and zeros, which can be faster and more efficient for certain AI tasks. We're seeing real progress in hardware built on these principles. Companies like Intel with its Loihi 2 chip, IBM and BrainChip are creating dedicated neuromorphic processors. Intel's Hollow Point system, based on Loihi 2, is currently the world's largest, boasting over 1 billion artificial neurons. These chips are showing promise for real-time learning and decision-making using far less power than traditional hardware. Devices like memristors and phase-change memory, or PCM, are crucial components, acting like programmable resistors that mimic how brain synapses learn and adapt. So why the big push? The advantages are compelling. The biggest one is energy efficiency, potentially orders of magnitude better than current CPUs and GPUs for AI tasks. This is huge for everything from extending battery life on your phone or wearable devices to making large-scale AI more sustainable. They also excel at real-time processing, vital for robotics, self-driving cars, and analyzing data streams as they happen. Plus, they can learn and adapt on the fly. The potential applications are vast: smarter AI, more capable robots, powerful computing on edge devices, advances in healthcare diagnostics, scientific discovery, and even faster fraud detection. Of course, it's not all smooth sailing. Building these systems at scale, ensuring they're reliable, and creating the right software and programming tools are significant challenges. Standard ways to even compare different neuromorphic systems are still being developed. But the potential is undeniable. Neuro-inspired computing isn't just about faster chips. It's a fundamentally different approach, inspired by the biological masterpiece that is the brain. It promises a future where computation is not only more powerful, but also drastically more efficient and adaptable, moving us beyond the limits we face today. Thanks for tuning in.